Hi guys, welcome to the next lesson. As ever, if you want to do these do now questions, please pause the video here and give them an attempt. I'll read the questions out now and then we'll go over the answers together. Question number 1 is, if you saw the chemical symbol for nitrogen written as N3 negative, what would this mean? If you saw the chemical symbol for nitrogen written as N3 negative, what would this mean? Number 2, if the electron arrangement for potassium, which is K, the chemical symbol is K, if the electron arrangement for potassium is 2881, what is the electron arrangement of K plus? If the electron arrangement for potassium is 2881, what is the electron arrangement of K plus? And number 3, if sulfur has an electron arrangement of 286, what would be the ion of sulfur most likely be and why? So if sulfur has an electron arrangement of 286, what would the ion of sulfur most likely be and why? So that question is really asking you, how many electrons does that need to be stable? And is it easier for it to lose or gain electrons based on that information? So if the sulfur has an electron arrangement of 2, 8 and 6, what would the ion of sulfur most likely be and why? Okay, pause it there. I've got that written as no now questions. That should be do now questions, obviously. Do now questions. Okay, here are the answers. So if you saw the chemical symbol for nitrogen written as N3 negative, what would this mean? Well, that means it has gained 3 extra electrons and become negatively charged. Okay, it's 3 times more negative than it was before. It has 3 extra electrons. Number 2, if the electron arrangement of potassium is 2881, what is the electron arrangement of K plus? And it would be 288. It's become positively charged because it has lost that extra valence electron. So it now has more protons than it does electrons, so now it is positively charged. And number 3, if sulfur has an electron arrangement of 286, what would the ion of sulfur most likely be and why? So it's most likely going to be, that should be 2s2 minus, with an electron arrangement of 288. It would gain 2 electrons as this is easier than losing 6. So its electron arrangement to begin with is 286. It only requires 2 additional electrons to be stable or have a full outer electron shell. So S2 minus or S minus 2 would be the most likely ion of sulfur. Okay, so hopefully that makes sense after the last lesson. In the last couple of slides in the last lesson, I talked about balancing chemical equations. And we did that by kind of counting the amount of atoms on one side, the reactants on the left-hand side, and then counting the products on the right-hand side. So we're going to do that in a bit more detail today and explain ways in which we can do that easily, because this can be quite a confusing part of chemistry that people don't understand or try to avoid because they don't really understand how to balance the equation. So we're going to look at how to really simple ways of being able to balance or just look at the equation and ensure that it's already balanced. So one of the things that we can look at here, we've got a few visuals, a few equations, okay? So at the top here you'll see reactant, and this is on the left hand side, these are the chemicals that are reacting, and these are the products on the right hand side that are going to be produced after this chemical reaction. So we've written the chemical equation and we've actually drawn it out as well. So you can see drawing it out is a good way to visualize it, but it takes a long time. But you can see here, if carbon is the black molecule here and hydrogen is the white molecule, we have C, which is just 1, and we have 1, 2, 3, 4 hydrogen, H4. So we've got 1 carbon and we have 1, 2, 3, 4 hydrogen. So we'd write that as CH4. If you look on the right hand side here, it says 2O2. So it says the word coefficient. It's telling us how many O2s are there. So we have 1 oxygen 2, so that's O2, and there's 2 of those. So it's 2O2. Okay, so there's 4 oxygen molecules here. 1, 2, 3, 4. And if you did 2 times 2, that would equal 4. Okay, so that's our reactants. So just so we have it clear in our heads, we have 1 carbon, 4 hydrogen, and 4 oxygen. So we must see that on the product side, on the right hand side, after the chemical reaction is done. So on the right hand side, we have got CO2 plus 2H2O. Right, so I'll admit when you first see that it doesn't look fantastic, but let's look at this. Let's just make sure that this is balanced. So we have C, 1 carbon, O2, we have 1, 2. So we have CO2, that's correct. Okay, we have 1 carbon and 2 oxygen, plus we have 2H2O. So we have H, so that's H2, and 1 O, and there's 2 of them, 2H2O. So we have 1, 2 oxygen here, and 4 hydrogen. Okay, so let's see if this balances out. We have CH4, so we have, remember we said 1 carbon and 4 hydrogen, and then we have 2 times 2 oxygen, we have 4 oxygen. Here we have 1 carbon, so that's correct, there's 1, that's balanced. O2, 1, 2, so we're missing another 2, but that comes over here, because 2 times O is 2 oxygen on this side and 2 oxygen on this side, so that's 4 oxygen. H2 times 2, 1, 2, 3, 4, so 2 times 2 is 4, so that balances out. We have 4 hydrogen on this side, 4 hydrogen on this side, we have 4 oxygen on this side, 4 oxygen on this side, and we have 1 carbon on this side, 1 carbon on this side. It's quite easy to see that when we look at the images as well, but what we need to do is just basically do the math in the equation and make sure they balance out. So don't worry, that's quite a lot of information. We're going to do some simple examples in this lesson and it should become clearer. So I'll just read this out. This is a kind of nice definition of what's going on. This example illustrates the fundamental aspects of any chemical equation. Number 1, the substances undergoing a reaction are called the reactants and their formulas are placed on the left hand side of the equation. So we've talked about that a little bit already. Number 2, the substances generated by this reaction are called the products, and their formulas are placed on the right-hand side of the equation. So hopefully that's not brand new information right now. We know that we have reactants here and products here. Plus signs separate individual reactant and product formulas, and an arrow separates the reactant and product left and right sides of the equation. So what are we talking about here? Well, these 2 things are separate molecules or compounds in this equation, and then when the chemical reaction is illustrated by the arrow, when they combine, then we get these products. When there's a chemical reaction, we get these products. Okay. The relative numbers of reactant and product species are represented by coefficients, numbers placed immediately to the left of each formula. A coefficient of 1 is typically omitted. So we know, what does that mean? We know there's 1 carbon here, so we don't need to write 1C. If there's no number in front of it, we know it's just 1. But here we have 2 loads of oxygen, so we have to put the number 2. Okay, so if it is just 1, we don't put a number. But if there's more than that, we have to then put a number to tell us how many there is there. Okay. So the equation for the reaction between methane and oxygen to yield carbon dioxide and water, so we haven't really used their names, I didn't think that was important right now, but it's confirmed to be balanced in this approach shown here. So the way we write it down here is CH4 plus 2O2 equals carbon dioxide and 2 waters. Okay? So that is balanced. Let's look at this again, just the way I did it, but we're going to break it down even clearer. So CH4, what we have here is a little table, and you guys will have this in your workbook. I'd like you to do this, work alongside me as I'm doing it. Okay? So we're going to look at the reactants first. The reactants is carbon for the first one. So we've got carbon as one of the reactants. 1 times 1, okay, so we're going to times that by 1, there's only 1 there, equals 1. In the products, how many carbons we got? We got 1 times 1 equals 1. Is this balanced? Yes. 1 equals 1. So 1 from the reactants and 1 from the products equals 1. So they are balanced. Okay. Hydrogen. We've got 1 hydrogen times 4. So 1 times 4 is 4 in the reactants. If we look at hydrogen on this side, we have 2 hydrogen times 2. That equals 4. Is that balanced? Yes, it is. 4 in the reactants equals 4 in the products. It's balanced. So this, so far, so good. Then we're going to look at oxygen. We have 2 oxygen times 2 equals 4 molecules of oxygen, atoms of oxygen. Products, we have a bit more complicated. We have 1 oxygen times 2. 1 times 2 equals 2. And then we have this number here, 2 times 1. 2 times 1 is 2. 2 plus 2 equals 4. So yes, 4 reactants equals 4 products. So it's balanced. Okay. You may want to pause that video there, and write in these answers if you are working alongside, and make sure that makes sense to you. Let's look at another really common chemical equation that we'll come across, and you may have come across already. And this is photosynthesis. The chemical equation for photosynthesis is sunlight and carbon dioxide and water leads to photosynthesis, which means plants can produce glucose, which is a sugar, plus oxygen. So basically all a plant needs is carbon dioxide, water and sunlight, and then it can produce glucose and oxygen. So that's really amazing. Every single food web relies on this formula because we as an animal species cannot produce our own energy. We need to take energy from other organisms. So we usually get energy by eating plants and animals. The animals that we get energy from have got their energy probably from a plant. So, for example, beef, you think of a cow on a field, it's getting all of its energy from eating grass, and the grass generates energy through this process of photosynthesis. So without photosynthesis, none of us would be here. And it's a really nice looking equation as well. You can see here 6 molecules of carbon dioxide plus 6 molecules of water, H2O, plus sunlight, you need sunlight to make the chemical reaction happen, results in glucose and energy. So we're going to do the same thing we did in the last slide, where we're going to look at each part of the reactants and products and make sure that they are balanced. So we're going to look at carbon first of all here. So here we have carbon, and we can already see we have 6 times 1 carbon. 6 times 1 equals 6. If we look over this side, we have 1 times 6 carbon, which also equals 6. Is that balanced? Yes, 6 does equal 6, so that is balanced. Now we're going to look at oxygen. So oxygen is a bit all over the place here. We have 6 O2, so it's going to be 6 times 2. For the first one, that gives us 12. Then we look at water, and we have 6 times 1 oxygen, so 6 times 1 equals 6. 12 plus 6 is 18. So we have 18 oxygens in the reactants. Do we have 18 oxygens in the product? Let's look. So we have O6, so 1 times 6. And then we have 6 times 2. So 1 times 6 equals 6. 6 times 2 equals 12. 6 plus 12 equals 18. And if you look at the reactants and the products, is it balanced? Yes, it is. 18 does equal 18. Awesome. Let's look at hydrogen. So we have hydrogen and H2O. Here we have 6 water molecules, so 6 times 2 equals 12. And then if we look on the product side, we have 1 times 12, which is going to equal 12. So let's look at that. In the reactants, 6 times 2 equals 12. Fantastic. In the products, 1 times 12 equals 12. 12 equals 12. Yes, it does. Fantastic. So this is the chemical equation for photosynthesis, which is really important. and it's nice and balanced as well when we write it like this. So I want you to do this in the table in your workbook just now, so you may want to pause that, and then we'll continue on. So I mentioned it again in the last lesson. Why do these chemical equations need to be balanced? Why can't we just have, a number of reactants on one side and a different number of products on the other side? Well, there's this thing I said last time called the law of the conservation of mass, and I'll talk about it again. But it turns out that matter can never be created or destroyed. It just changes its form. So you can't destroy those carbon atoms, those hydrogen atoms, and those oxygen atoms. You can rearrange them in different ways, but you can't destroy them. So if you can't destroy them or create new ones, then they have to be somewhere in the chemical equation. So it has to balance on both sides. Let's look at oxygen and hydrogen, which forms H2O, water. So we think of water, we know that it can change forms as well. So when water is below 0 degrees, it freezes, has a freezing point of 0 degrees. When it's melted, it's liquid, and we use that most often. And then above 100 degrees Celsius, it evaporates but turns into water vapour. So although it changes form, it's never destroyed. And this is a nice little way to think about how chemical reactions happen. Nothing is ever destroyed. It might just change the way it looks, but the same amount of stuff should still be there in terms of the number of atoms in the chemical equation. So who do we need to thank for that discovery? Well, it was a guy called Antonin, I can't say his name, we'll go for Anthony, Lavoisier, and he was a French chemist. And he came up with this law of conservation of mass, which says the total mass of any material system is neither increased or diminished by reaction between the parts. So what he's saying there is the total number of products and reactants have to equal one another because neither one is destroyed. So when we have a chemical reaction, it may look like something blows up. It may look like, it completely changes the way it looks, like water can turn into gas, but the same volume of it is there, okay? The same numbers on each side. It's always balanced. We cannot create or destroy matter. And we're going to be talking about that in a lot more detail, but hopefully now that's something in your head. It's called the law of conservation of mass. So what does that mean, conservation of mass? You've maybe heard of the word conservation before, particularly when we talk about animals and habitats. We want to conserve their habitats. When we conserve something, we protect it. So basically what we're saying here is the mass, the weight of the chemical equation is always protected because of this law. The law states that nothing can be created or destroyed, therefore mass is always conserved. That's where the name comes from. Okay, this is a bit of a gross one from Hamish. Most lipstick contains fish scales. Lovely. Thank you guys, we'll see you in the next one.